In this video, we are talking about a rehabilitation design of an existing pavement. This road is located in Farrelly Highway in Western Victoria, and the subject is to evaluate two lanes of this road westbound of the carriageway. The width of each lane is 3.5 meters, and on the other side of the road there are 1 meter sealed shoulder with a 40 millimeter thick asphalt. This pavement is supposed to be re-evaluated for the traffic load of 2 by 10 power 6 ESA for inner lane and 4 by 10 power 6 for outer lane. The structure of the existing road is, as you can see, 50 millimeters of asphalt on the top layers, 75 mils of asphalt leveling course, 175 granular base course, 200 millimeters granular sub-base, and 300 mil select fill. The base course and sub-base, they both have a very good value of CBR. And we need to go further and see what we can do with these material. The deflection surveys also was provided, and as you can see in this table, for every 100 meters we have the average deflections, and we have the CV, which is coefficient of variations. But for the purpose of our design, we ignore this average and we go and start by making a lot. But as you can see in these tables, the roughness values RI also has provided. So I highlight the chainage 1300 and 1400, and you can see the IRI, it's really high. And we assume in this section of the road, maybe we had some patching. So that's why the roughness is changed. So we need to think about what we can do with these sections. Also in the from chainage 3300 up to the end of the road, we have a high value of roughness too. Here we show all the data, the deflection data. As you can see, it is clear enough. We can split these data into lots, lot 1 and lot 2, and to split the lots, it's important to have the coefficient of variation less than 25%, which is the average of the deflection divided by standard deviation of that data. So after we split our lots and find out where the lot is, we should go and check the characteristic of deflection and work out that value. For characteristic deflection, we need to have the average deflection and standard deviation, and the factor F, which we choose 1.65 because the road is a highway. We also need to work out the characteristic of curvature, because for the asphalt overlay design, we need to check the fatigue for the asphalt. So we summarize all the calculation in the table, and next step we're going to compare the characteristic deflection with the design deflection. And if the CD is lower than the design deflection, that means we don't need to do any overlaying. But if it's over that, we go and do the overlaying. So keep in mind, as an option, we check the milling as well, 40 mil milling. The Ostrode says when for every 25 millimeters of milling, we need to raise CD by 15% and CC, which is characteristic curvature, by 25%. As you can see, the design deflection for inner and outer lane were obtained from this graph. For the inner lane, we get 0.98 millimeters, and for outer lane is 1.07 millimeters. As you can see, the first lot has the design deflection more than the CD, which means there is no need for overlay design. So we go and check the allowable traffic loading and see if it's greater than design traffic loading or not. If it's not, then we need to do the overlay. But as you can see in the graph, both inner lane and outer lane, they're both located in we have higher allowable traffic loading. So we are good. Next, we go and check the second lot. But in the second lot, we have the CD more than the design deflection. So we need to go and find the suitable asphalt overlay thickness. So we have in the table, as you can see, we put all the thickness which we need for after milling or without milling, and for inner and outer lane both. We keep it here, and we go to check the characteristic curvature as well and see if that thickness is good enough or not. So, when we check the characteristic curvature graph, we can see we need more thickness than the ones we get from the characteristic deflection chart. So as you can see, the thickness we get here is really high, and as we want to keep this section of the road as same as level as what it is, because it's gonna end up at Saltwater Creek Bridge, so we don't want to change the level. So it is not really practical to doing the overlay in this section. So we go and do check if with the excavation and put a layer of asphalt on top, and we go and check different design chart and choose the best option which has the lowest cost. So here we have go through the option A. For option A, for chainage 0 to 3300, we suggest have 40 millimeters of milling, then put back 40 mil of asphalt. For the section of the chainage 1300 to 1500, we want to use the asphalt with the binder A15E, and for the rest we using the conventional binder. The reason to use A15E binder is at that section we have a high roughness, so we want to raise the quality in that section, and we assume this binder can help as it will be raise the allowable traffic load by 2.5 times what we're reading from the characteristic curvature chart. For the last section of the road, the lot 2, the option is excavate and remove 125 mil, which would be the existing asphalt layers. Then do the stabilization of the existing layer of pavement, but it's different from inner lane and outer lane because the traffic load is different. And then turn back 125 mil of asphalt with the conventional binder. And we keep going with 40 mil milling and turn back 40 mil asphalt every 5 years. For the purpose of stabilization, we're using the cemented material with modulus of 2000 MPa. So now we go to option B. For option B, For the first lot, I suggest just to put 25 mil of asphalt on top of the existing surface. Actually, we just want to do that because we want to correct the shape of the existing surface and also have the better quality on ride. For the second lot, what I assume is to do the excavation 170 mil of existing surface and then put back 170 mil of asphalt. Here I use the design chart, which is shows the subgrade of it modulus of 70 MPa, and then unbound granular on top of it, then the asphalt. So I assume the granular that we have, we can use it. And I just stick to the asphalt overlay, asphalt that we need to put it on top. So for outer lane, I assume we have 375 mil of unbound granular, and I work out we need 170 mil of asphalt. So for all that section, we put 170 mil. And then we carry on with the every 5 years, do the 40 mil of milling and then put 40 millimeters of asphalt on top of it, so we don't change the level of the pavement. Now we are going to work out the whole of life cost. You can see the equation. In this equation, we need first to work out the cost of the initial construction or the rehabilitation we wanted to do. And then the M, which is cost of the maintenance. And then R, which is the real discount rate, which we have 4% in our job. And X, it shows the number of years from the date of opening the road to the traffic. And Z value is the analysis period, which we have 20 years. And as a salvage, we assume the salvage is 0 here because you're thinking the option A and option B has the same value. It doesn't really affect our calculation here. But before we going further, we need to adjust the unit rate to our design because, for instance, in this table on the left hand side, it said excavation and removal of material, which is $25 per square meters for 250 millimeters, but we don't have that much, so we need to adjust it. For example, here for 125 mil in the right hand side on top, we put 70 dollar for each square meters because it's not really become half price because still they need to have the machines and bring stuff or turn back stuff. It doesn't look like to just have the interpolation for the costing, but we're assuming just some value here. As you can see in this table, we work out the cost of construction and rehabilitation. In the first column, we have the year. In the second one, that's a job description. And in third column, we have the unit rate is C, which is the present cost of initial construction. Then we have routine maintenance cost. Then we add them together. After that, we use the PWOC equation with the rate of 4%. The same for option B. Finally, we have the total value. As you can see, option B is much more cheaper. It's about 24% lower than the option A. We can choose the option B as a rehabilitation method. So if you want to summarize the job, you can understand that the section 300 to 1500 chainage, we have the high value of roughness. So we put 25 millimeters on whole section, on whole lot, and we fixed the roughness in that section. Also, as we have a very high quality of granular, we don't know about the PSD, but with the CBR, we're just assuming that the granular existing pavement is valuable, and we use it in our design. And we just do the excavation, 170 mil, and then put 170 mil of asphalt. I hope you enjoyed this video. Bye.